Generally, spray application is the best method to use for the rapid application of coatings to large surface areas, and for the highly uniform application of most coatings in nearly all situations. There are two major types of spray application equipment. Conventional airspray. The coating is atomized by a stream of compressed air and is carried to the surface on a current of air. Both air and coating enter the gun through separate passages, channels, are mixed and are driven through the air cap in a controlled spray pattern. Airless spray. The coating is atomized without the use of compressed air and is carried to the surface by the power of the fluid pressure passing through the spray gun. The coating is pumped under high pressure to the airless spray gun, where it is forced through a precisely shaped and sized opening called the orifice or spray tip, as it is being driven to the surface. Both conventional airspray and airless spray equipment may form the basis for modified equipment for special use situations, including plural component spray, hot spray, electrostatic spray, centrifugal spray, HVLP, high volume, low pressure spray, air-assisted airless spray. We shall study these more complex systems and equipment in the advanced module on coating application. We shall also study other methods of coating application, including powder coating, flame spray, spray metallizing, dipping, barrel coating, flow coating and roller coating, electrophoresis, conventional airspray advantages. Spray pattern is easily adjusted to almost any desired fan width. High quality finishes, such as for automobiles and furniture, can be produced. Conventional airspray disadvantages. High loss of coating is caused by overspray. Billowing and air turbulence are created by the compressed air required. Reduction of coatings with solvent is often necessary for proper atomization, resulting in lowered DFT per application. Airless spray advantages are overspray and bounce back are reduced, resulting in material savings. Heavier film builds are possible with most coatings. Compressed air is not required to atomize coating. Pressure pot is not required. Equipment can also be powered by air, by electricity, or by hydraulics. Production rate is much faster. Coating may be driven into crevices, cracks and corners. Airless spray disadvantages are: the fan width of an individual spray tip is fixed, not variable. There is little control over quantity of coating applied except by changing tips. Because of the speed of the fluid flow, it is difficult to coat small, intricate items. Conventional spray is widely used for high-quality finishes, for example, car spraying, but it is relatively slow and provides a low film build. High-build coatings can be sprayed using conventional spray equipment, but the material generally requires thinning to pass through the gun at the relatively low pressures. Conventional spray is widely used in some parts of the world for a broad range of coating applications. Some users continue to use conventional spray equipment because it is safer and less hazardous for the applicator. For the industrial user, however, only the high-pressure conventional equipment is of interest, and then only for particular uses. For example, application of zinc silicate on intricate shapes, where control of the spray pattern is important. In general, the use of conventional spray equipment has largely been replaced by airless spray for application of most industrial protective coatings. In Europe, conventional spray is rarely used. In the USA and some other countries, conventional spray is more widely used, particularly for coatings such as inorganic zinc, or where finish appearance is important. The purpose of this overview is to discuss safety hazards found in all spray operations, regardless of what specific types of spray equipment are used. Specific cautions for each piece of spray equipment will be addressed when that piece of equipment is discussed. The danger from toxic or fire hazards should always be in the minds of the coating inspector, as well as supervisors and workers. Most workers are usually aware of the hazards from mechanical equipment, cranes, ladders, staging, etc. However, they may not realize the tremendous damage that can result from a small quantity of vaporized volatile solvent, an explosion hazard, and they must be made aware of the dangers to health inherent in fume and dust exposure. Workers have been killed by explosions that were due to painting in confined places. One accident occurred when the workers were being supplied with fresh air through proper masks because of the toxic hazard, but the concentration of vapor in the air space was in the explosive range. An extension light bulb broke and ignited the vapor, killing several men. Flashpoint is an indication of the fire or explosion hazard of a flammable solvent. A surface may be hot enough to volatilize sufficient solvent to cause a localized danger. Sprays and mists can be very dangerous. Even finely atomized metals or dusts may explode when dispersed in air. Coatings and their solvents are sometimes categorized according to their flashpoint temperature. Low flashpoint solvents are those with a flashpoint below typical storage temperatures, 73 degrees Fahrenheit, 23 degrees centigrade, and are the most hazardous to store and/or use. Adequate ventilation is essential to keep the solvent content of the air below the lower explosive limit, and also to facilitate curing of the coating. Spray finishing creates a certain amount of overspray, hazardous vapors and toxic fumes. This is true even under ideal conditions, and there is no way to avoid it entirely. Anyone who is around a spray finishing operation should consider some type of respirator or breathing apparatus. A respirator is a mask worn over the mouth and nose to prevent the inhalation of overspray fumes and vapor. Respirators are necessary for two reasons. First, some sort of respiratory protection is dictated by regulations. Second, even without regulations, common sense determines that inhaling paint overspray and solvent fumes is not healthy. Even though the concentration of flammable gas or vapor may be below the lower explosive limit, it may be far above the safe limit for breathing. The maximum allowable concentration is the amount that must not be exceeded when a worker is exposed to the hazard for an 8-hour workday. This concentration pertains to vapors, gases, mists and solids. Maximum allowable concentrations, NACE, are published annually in the USA in the Archives of Industrial Hygiene. These same NACs are often adopted in other countries. In general, the aromatic solvents, such as xylene and toluene, are more hazardous than the aliphatic solvents, such as mineral spirits. Unfortunately, mineral spirits are rarely used in high-performance coatings, and relatively hazardous solvents are still widely used. Aromatic solvents are used almost exclusively in some synthetic paints, such as lacquer and vinyls, and to a greater or lesser degree in oleoresinous paints, such as phenolic varnish and some alkyds. Allowable concentrations for the aliphatic solvents are greater than for the aromatic solvents, but in every case, the maximum allowable concentration for breathing is far less than the lower explosive limit. This means that while an airspace may be considered safe from fire or explosion, it might be extremely dangerous to personnel. The exposed workers should be supplied with fresh air masks connected to a source of clean, cool, filtered air. The common practice of using low flashpoint solvents such as MEK or acetone as universal thinners can be extremely hazardous, particularly in enclosed spaces. Spray painters in particular should be protected against breathing dangerous concentrations of paints containing lead or chromate. Brush painters are also exposed to these hazards. In addition to being supplied with adequate ventilation, spray removal, respirators and air filters, workers should clean themselves thoroughly before eating and before leaving the job. Contaminated clothing should not be reused until thoroughly cleaned. When air-supplied respirators are used, it is critical that the air supplied is fresh and pure. The common practice of using plant air, air taken from a factory supply, can be dangerous if the air is contaminated by the compressor or an operation elsewhere in the plant. Filters and warning monitors should always be fitted in line before the air is used by the sprayer. There are 4 primary types of respirators available to protect the operator: air-supplied hood, air-supplied mask, organic vapor, dust. Hood respirators are designed to cover the entire head and neck area and supply the wearer with clean, dry air at low pressure through a filtered air supply. They protect the wearer from heavy concentrations of vapor, fumes, dust and dirt that might prove harmful to respiratory organs, eyes, ears and exposed skin. They are used where other types of respirators are impractical and do not provide sufficient protection. The hood respirator provides the most complete means of protection because it offers eye, ear and skin protection. The continuous supply of dry, fresh air prevents misting or fogging in the hood. Air-supplied respirators are commonly required when coating work takes place in confined spaces, such as tanks, and may be mandatory when certain coatings, for example those containing isocyanates, are spray applied. The air-supplied mask respirator covers the nose and mouth only and operates from an external supply of air. It does not provide the degree of protection against splashes, etc., that can be achieved with a hood respirator. Eye protection, such as goggles, must also be worn if this type of respirator is used. The organic vapor respirator covers the nose and mouth and is equipped with a replacement cartridge designed to remove the organic vapors by chemical absorption as illustrated. The correct cartridges must be used. Some of these are also designed to remove solid particles from the air before the air passes through the chemical cartridge. It is usually used in a finishing operation with standard materials and is not recommended for use in commercial coating operations. To be effective, there must be a complete seal between the mask and the face. Separate safety goggles or other eye protection must be worn when required. Records of respirator use should be maintained, since the cartridges have a limited life and must be replaced. Dust respirators are sometimes used by sprayers or helpers, but in most applications they are not effective and probably illegal. These respirators are equipped only with a cartridge to remove solid particles from the air, such as in preliminary surface preparation operations, like sanding, grinding or buffing, and are not designed to remove vapors. separate safety goggles or other eye protection must also be worn when required. Safety recommendations for proper personal protection equipment, PPE, can be found on the coating manufacturer's Material Safety Data Sheets, MSDS, and specified clothing, masks, etc. should always be worn. Further information on these issues can be found in the Basic Safety module of this course. Air control equipment is any piece of equipment installed between the air compressor and the point of use that modifies the nature of the air stream. Air control equipment can modify or control the volume of air, air pressure, cleanliness of air to the spray gun, distribution of air to multiple pieces of equipment. Air control equipment is often collectively known as the air transformer, also called a filter or regulator. This multi-purpose device removes oil, dirt and moisture from compressed air, regulates and indicates by gauge the regulated air pressure, provides multiple air outlets for spray guns and other air-operated tools. The principal parts of an air transformer are air condenser, a filter which is installed in the air line between the compressor and the point of use. It separates out such solid particles as oil, water and dirt, and cools the compressed air. The air condenser is not capable of regulating air pressure. Air regulator. This device reduces the mainline air pressure as it comes from the compressor. It automatically maintains the desired air pressure with minimum fluctuations. Regulators should be used in lines already equipped with an air condenser or other filtration device. Air regulators are available in a wide range of air volumes and pressures, with or without pressure gauges, and in different degrees of sensitivity and accuracy. They have main air inlets and regulated air outlets. An air pressure gauge, which indicates the air pressure. Outlet valves, which provide shut-off of individual lines. A drain, which is used to vent the accumulated water, oil and dirt from the condenser. Lubricator. Some air-powered tools require a very small amount of oil mixed in the air supply that powers them. Lubricators are often combined with air filters and regulators in a single unit. The operator should ensure that the air supply for conventional air spray equipment does not contain a lubricator. When air-powered tools are being used, Oil allowed to fall on the prepared surface would clearly be a problem. Both the operator and the coating inspector must check to see that oil is not applied to the surface. Good practice recommends that lubricators for air-powered tools should be on a branch line separate from lines supplying air to spray applications. The air transformer, filter or regulator and condenser should be drained or cleaned at least twice daily, depending on the humidity and system usage. In humid areas, or where the system is used heavily, more frequent cleaning, draining will be required. Moisture or oil in the spray atomization air will ruin a coating job. The air must be clean and dry, and oil and water removed from the air supply. Condensation is often likely due to pressure changes as the compressed air is released to the atmosphere. As with blast cleaning equipment, airlines are likely to contain moisture from the previous day's work and should be dried at the start of work each day. The compressor should run long enough to warm up and reach operating temperature, and the air checked for oil and water using the blotter test, for example, ASTM D4266. If moisture passes through the air transformer or air condenser, the operator should check the following and see that corrections are made as necessary. Drain filter, regulator, air receiver and airline of any accumulated moisture. Make certain that the filter or regulator is located at least 25 feet, 8 meters from the compressor. See that main airline does not run adjacent to any steam or hot water piping. Ensure that the compressor air intake is not located near steam outlets or other moisture-producing areas. See that the outlet on the air receiver is located near the top of the tank. If the compressor is water-cooled, check for a damaged cylinder head or leaking head gasket. Intake air should be as cool as possible. Check pressure gauges to ensure that they are readable and accurate. Most equipment that can be calibrated should carry a calibration sticker, particularly if an ISO 9000 quality system is operated by the applicator. Conventional airspray equipment used for application of industrial protective coatings generally contains all the following components. Air compressor, which provides a continuous supply of compressed air to the material container and spray gun. Air control equipment, which helps provide a steady supply of clean, dry air. Hoses, which transport air and coatings between the compressor, spray pot and spray gun. Spray pot, which contains and holds the coating to be applied. Conventional airspray gun, which mixes air and coating and applies the mixture to the workpiece in a controlled spray pattern. The air hose is usually red, although in a small low-pressure system it may be covered with a black and orange fabric. The air hose transfers compressed air from the air regulator to the gun. Air hoses should not be used for coatings. The internal diameter, ID, of the hose from the regulator to the spray gun should be a minimum 5/16 of an inch, 8 millimeters, although larger sizes are not uncommon. If the air hose ID is too small, the spray gun is starved for air because of excessive pressure drop, which can result in a variety of spray defects. The fluid hose is usually black or brown rubber and is electrically conductive so that the system can be grounded. Since solvents in coatings can readily attack and destroy ordinary rubber compounds, the fluid hose is lined with special solvent-resistant material impervious to common solvents. Note, some fluid hoses made of clear plastic are now available. For normal finishing, 3/8 of an inch, 10 millimeters ID hose is suitable. Guns used in maintenance finishing work may require a 1/2 inch, 12.5 millimeter ID hose. High viscosity materials could require 3/4 of an inch, 20 millimeters to 1 inch, 25 millimeters ID material hose. Fluid hoses are generally cleaned by running appropriate cleaning solvent through the line at the end of the working shift. Sufficient solvent should be used to remove all the coating material. The operator will generally judge the effectiveness of cleaning by the color of solvent as it is cycled through the line. The fluid hose can be cleaned using a hose cleaner, which forces a mixture of solvent and air through the fluid hose and guns, ridding them of coating residue. A valve stops the flow of solvent and allows air to dry the equipment. If cleaning is not adequate, coatings which cure in the line will either lead to blockage or reduced ID of the line, or more likely will be softened by other solvent used subsequently and contaminate other coatings or block the lines and tips. The outside of both air and fluid hoses should be wiped down with the appropriate solvent at the end of every working day. Hoses should be stored by hanging in neat coils, cleaned properly and cleaned regularly. Hoses should not be dragged across the floor, pulled around sharp objects, run over with a vehicle, kinked or bent, used as a rope for lowering persons or equipment from scaffolding. Coating materials must be delivered to the spray gun. In this course, we'll discuss only pressure feed material supply, pressure feed airspray guns. The other types, including suction feed and gravity feed, are rarely encountered in industrial coating operations. Common types of material containers include cups that attach to the gun itself, remote pressurized tanks located away from the gun, cup guns, cups fitted directly to spray guns are necessarily small and must be refilled frequently. They are more likely to be used for small operations and for fine finishes on small components, so are infrequently used for application of industrial coatings. Cups may be pressurized or may be used to provide material for suction feed or for gravity feed equipment. Pressure feed tanks are closed containers ranging in size from about 2 US gallons, 7.5 litres, to 120 US gallons, 450 litres, that provide a constant flow of coating material at uniform pressure to the spray gun. The tank is pressurized with compressed air, and fluid is forced out of the tank through the fluid hose to the gun. Increasing or decreasing the air pressure in the tank controls the rate of fluid flow. Pressure feed tanks provide a practical, economical method of feeding material to the gun over extended periods of time, and are generally used where continuous production is to be maintained. The flow of material is positive and uniform. Relatively high viscosity and high solids coatings can be applied in this way, but generally not 100% solids coatings. Tanks can be equipped with agitators that keep the material mixed and in suspension. A typical pressure feed tank consists of the shell, a clamp-on lid, the fluid tube, the fluid header, regulators with gauges, safety relief valve, agitator. The construction of pressure feed tanks varies according to the service for which it will be used. Light-duty tanks are usually made of welded steel and have inlet air pressure restriction. Heavy-duty tanks are ASME coded and made of drawn steel. When abrasive or corrosive materials are to be sprayed, the tank shell used should be coated or lined with some special material. An insert container can also be used. Pressure feed tanks should be equipped with regulators for 3 primary reasons. The regulator allows material flow to be constant and regulated accurately. Regulators provide adjustment capability to accommodate a wide range of material viscosity and permit pressure increases when added hose lengths demand it. Regulators allow more adjustment of the balance between the material flow and the atomization air pressure. Pressure feed tanks may be fitted with a single regulator or a double regulator. The double regulator should always be used in industrial spray applications. One regulator controls the air pressure on the material in the tank, thereby controlling fluid flow, and the other controls atomization air pressure to the spray gun. Both controls are at the tank near the operator and can be adjusted for any operating condition. The fluid pressure may be higher or lower than the atomization air pressure. This depends on the factors shown here. Pressure feed material tanks and insert containers should be completely cleaned inside and out with an appropriate solvent after every use. Cleaning while the paint is still wet is obviously the most efficient method. When cleaning a pressure feed container, clean and inspect the sealing surfaces, gaskets and clamps. The piece of equipment that delivers the coating to the workpiece is the spray gun. There are two very broad classes of spray gun: automatic and manual. Automatic guns are generally identical in operation and specifications to the manual guns. They are mounted on a fixed or moving apparatus to paint objects which are usually carried past them on a conveyor. Automatic guns are triggered by remote control through an attached air cylinder and are pre-adjusted to spray the correct mixture for a good finish. The specific uses and details of automatic spray application are covered in the advanced module of this program. It should be noted, however, that many manual spray concepts and tools are very similar to those used in automatic spray applications. The spray pattern and density are adjusted using various valves and control devices on the gun. A manual gun is held by an operator who triggers the flow of air and material. The material is applied when the operator aims the gun and pulls the trigger. Operator technique is important to producing a fine finish. The principal components of a typical manual airspray gun fall into three main categories: control of airflow, control of fluid flow, and the gun body. Here are some of the major airflow parts. The air control valve is located in the gun's handle, directly behind the trigger. When the trigger is pulled, the air control valve opens, allowing air to pass through the gun. A positive return spring in the stem of the air control valve keeps the valve closed until the trigger is pulled. The air control valve provides no air pressure regulation. When the air valve is closed, no air enters the gun. When the valve is opened, the full air pressure is admitted. The air pressure is entirely controlled by a pressure regulator located between the compressor and the gun. The air pressure should be adjusted according to the viscosity of the material being sprayed and the desired density of the spray, light or heavy coverage. An air-adjusting valve or screw is provided on some low and medium volume guns and is included as an option on high volume guns. When the valve is Built into the gun, it is located adjacent to the air inlet at the base of the handle. When included as an option, the valve is placed at the air inlet connection, in line with the air hose. The air adjusting valve controls only the flow of air, cubic feet per minute, liters per minute, and has no effect on air pressure, pounds per square inch, MPa. The pattern adjusting valve or screw is located at the back of the gun. It is the top of two knurled knobs found there. The stem of the valve seats in the front of the gun, in either an air baffle or air port. The pattern adjusting valve regulates air supply to the horns of the air cap. The horn air controls the shape of the spray pattern. When the valve is closed, turned completely clockwise, a round spray pattern results. As the valve is opened, turned counterclockwise, an increasingly narrow fan pattern develops. The air cap directs pressurized air into the coating for atomization and onto the coating via air horns to control the shape of the spray pattern. Industrial airspray guns are commonly referred to as either internal or external mix. Both types may be used in manual or automatic operations. Internal mix guns combine air and coating material inside the air cap. The material is atomized prior to leaving the gun. Internal mix guns must be used with a pressure supply, so suction feed or gravity feed are not possible. They are generally used when a coarse finish is required, such as sealing texture spray and mastic roof coatings. Atomization air and material pressure must be approximately equal at the gun. The fan pattern is determined by the shape of the air cap opening. Internal mix guns, also known as low-pressure guns, are generally used when only a low-pressure compressor is available, or when slow-drying or viscous materials are used. Fast-drying materials would tend to plug the gun's cap hole. External mix guns combine air and coating material just outside the fluid tip. Air atomizes the material as it leaves the gun. External mix guns may be supplied by either pressure feed or suction feed sources. External mix guns can be used with either suction or pressure supply. They're used when a fine painted finish or versatility is required. They are a widely used type of gun because they provide better atomization and more control than internal mix guns. Once the equipment is hooked up, the pressure feed gun must be balanced. Use the steps shown here. Once the gun is balanced and ready to spray, good spray technique is required to produce an acceptable coating application. After the coating operation is finished, correct cleanup is necessary to ensure that the equipment will be in good working order for the next job.